Okay, so off we go. Here's where we were last time. We were talking about boundary flux. Remember the idea of two-dimensional flux? It's pretty much the same as the idea of two-dimensional flux. It's just that if your fluid is a two-dimensional thing, then it doesn't flow through surfaces. It flows across lines, right? So analogous to otherwise. And what we argued last time was we did some sort of trickery, and we noticed that this dot product and that dot product were the same. And so after having written this, to suggest that, the total boundary flux is we're just going to add up what we get along every piece along the entire boundary. And on each piece, we have this nice easy formula on the previous page. Our little geometric trickery up there allows us to rewrite that as this. And then, of course, T ds is dx. And lo and behold, what we find is we can compute flux with a regular old vector line integral. And I believe this is where we ended last time. Okay. So how are we going to compute that vector line integral? Now, we have various tools for how to compute vector line integrals, and we're going to be developing more today. But anyway, for the moment, what's really convenient about this vector line integral representing the total boundary flux is that, it's a vector line integral on a boundary. That's our condition. Aside from some regularity concerns. This is our main condition, though, for being able to compute this with Green's theorem. And so you'll notice that's the very next thing I write down here is Green's theorem. Let's see, let me zoom in a little bit better here. Okay. Now, in particular, this is a little bit awkward. This is not the regular statement of Green's theorem. This, of course, is as applied to that vector field, the vector field you get when you turn the original vector field 90 degrees counterclockwise. So, likewise, it is that vector field that I have to compute Green's operator of. So, okay, we've got to be a little bit careful when we write down Green's operator. Remember, Green's operator, y'all probably have already memorized the little formula for it, dq dx minus dp dy. Remember, don't get distracted by alphabetical order, right? Stuff like that. It's the x partial of the second coordinate minus the y partial of the first coordinate. So keeping in mind x partial of the second coordinate, well, our second coordinate is p, right? And then minus the y partial of the first coordinate, well, our first coordinate is minus q. Right? So when we say we want to compute Green's operator of this vector field F perp, that's what it ends up being. All right. And then you move around some minus signs and blah, blah. And what we find pretty quickly is that we have, in fact, a double integral of dp dx plus dq dy, and that, in fact, is our definition of two-dimensional divergence that we saw back in Chapter 3. Yeah.
Could you go over, I know this is partially related, could you go over the boundary condition one more time that helps you?
Oh, yeah. No, that's right. So this is, let's go back to our statement of Green's theorem. Here it is. And a lot of people mistakenly think that whenever you have a vector line integral, that you can always just rewrite it as a double integral of Green's operator. And that's importantly not true, right? So the whole point is, and it says so right here, right? This has to be a boundary vector line integral. In other words, this has to be a circulation specifically. That's all that was. Is that cool? Yeah. Okay. Right. Okay. So let's see here. Let me if I can get this to cooperate. There we go. Okay. Back to let's see. Oh no, too far. Here we go. Okay. So altogether we have computed boundary flux. And we've got this as our result. So if you have a vector field, you want to compute the outward-oriented boundary flux through the boundary of that two-dimensional region. Here you go. Here's a double integral over the region itself. and your integrand is divergence. So this is sometimes called the two-dimensional divergence theorem, which is what I've written here. But now let's also recognize, to be fair, right? Most of the heavy lifting here was done by Green's theorem, right? We did a couple of, a little bit of trickery at the beginning and a little bit of computation, plug and chug at the end. But mostly this is Green's theorem doing the work. And so a lot of people instead will view this as an alternate version of Green's theorem. Perfectly reasonable point of view as well. Okay. All right, so let's do one. And here's just, this is a pretty brute force example. The question explicitly asks us to compute the boundary flux, right? Well, it says flux, but that said, it's a flux through a curve that is a boundary, and furthermore, outward, as is our convention for what we mean by boundary when you're talking about flux on a curve. So we can interpret the question, let's say, as outward-oriented boundary flux. So I'm going to compute this exactly as the formula above says. We were asked to compute flux, and we're going to do it with the 2D divergence theorem. In other words, a double integral of divergence. Having realized that, all I've got to do is take my vector field. That vector field, compute divergence. This is, again, just a pat formula. We're going to take the x partial of the first coordinate. We're going to add the y partial of the second coordinate. Those numbers turn out to be super nice. We end up with a really easy integral and answer. Okay. How we doing? Everybody all right on that? Okay. All right. Okay, now here's a different point of view you can take on that theorem. And again, yes, we do have technically a new theorem here, but again, Green's theorem did most of the work. So could I have gotten to this result without piggybacking off of Green's theorem? And it turns out that absolutely, you definitely can. There's some details that have to be dealt with, but it's mostly just computations that we're not going to bother with anyway. The key point, the thing that makes it all come together, is exactly the same thing that makes Green's theorem come together, and that is that we have an accumulating quantity. Now, with Green's theorem, we were talking about circulation, boundary circulation. As it turns out, boundary flux also accumulates over areas. So remember what it means to accumulate over areas is the whole is the sum of the parts. So in particular, if I were to look at the outward oriented boundary flux of D1 here, and if I were to look at the, again, outward oriented, so outward from D2, outward oriented boundary flux on D2, and outward from D2 is that way. Outward from D1 is that way, right? So you can see this looks a lot like the overall outward-oriented boundary flux, with the main difference being all this stuff that's happening in the middle, right? We have this shared edge that was created when I sort of sliced right through the middle of my lump to divide D1 from D2, and on that shared edge, yes, there are new flux terms, right? On this shared edge, there is a part of the boundary of D1 flux term that way, and there is, on that same shared edge, outward from D2 flux term as well. And morally, just like we saw with the analogous argument with circulations, same edge appears twice with opposite orientations, which therefore have exact negative values of each other, and they cancel. So it's a really beautiful little fact. These cancel because the two different orientations through the curve were opposites. When we were talking about Green's theorem and how circulation accumulates. It was the fact that these two terms had opposite orientations along the shared edge instead of through the shared edge. So, yeah, it's geometrically different, right? But nevertheless, it's orientations that give rise to this oppositeness on shared edges, and that's what makes it all work. So, geometrically different, but morally equivalent. And I'm going to get back to where I was. Yeah, here we go. Okay. All right. So, here's a quick summary of what I'm going to call accumulation theorems that we have collected so far, and we're going to add, let's see here, kind of 2 more of them today. A lot of stuff to talk about. So what I'm going to call the very first accumulation theorem we ever wrote down, it wasn't even really a theorem, it was an example, kind of a motivating example, one could argue, of what's a double integral and why do we care? And one of our very first examples was to observe that, if you're interested in mass that's distributed over an area, holds the sum of the parts. So I can write this down. Right? This, of course, is just a shorthand for a Riemann sum, where I'm literally viewing the whole as being the sum of the parts. And then I make a density argument that on each little piece, stuff per unit size relates by way of density, right? Stuff per unit size is what you multiply by size to get stuff. Right? Okay, so, but we also have these other 2 theorems, and these other 2 theorems are very geometrically different, right? These aren't even physical, right? Our first example up here was about a physical quantity called mass. This is not really a physical quantity. This is about this mathematical construction called circulation. And the one down here is about a mathematical construction called flux. And, physical interpretations, sure, I suppose. But they're not really physical things. But they accumulate. So the whole is the sum of the parts, just like with mass. And on each little piece, we're talking about stuff. And stuff relates to size by way of stuff per unit size. So it's the same basic idea. So in the same way that this mass per unit size is mass density, well, this is just circulation per unit size. So it's circulation density. And this is just flux per unit size. So it's flux density. By the way, this is a very common term right here. And in my past life as a physics major, I heard this phrase, flux density, I'm going to say significantly more than I heard the term divergence. So, y'all being mostly engineers, I think you're probably going to hear this term flux density regularly, if I had to guess, sometimes at a minimum. I feel pretty confident, and you're going to need to understand why they call it flux density. Well, this is why. It's because it's an absolute pattern identical rip-off of the idea of mass density. Okay, how we doing? Everybody okay with that? Okay, so next, accumulation theorem. Good news, it's one you already know. You probably didn't think of it in those terms at the time, but we're going to talk about the fundamental theorem of calculus. I'm going to take a particular point of view on the fundamental theorem of calculus. I know y'all know the fundamental theorem of calculus, right? But I think there's a lot of value in being able to see how it's morally equivalent to the theorems that we just wrote down, right? So I'm going to take this, again, this particular point of view on it, not because you need it for stuff you've already done, but because it's going to help you connect to things that we're doing now and to things that we'll be doing over the next few weeks. So I'm going to point out that the fundamental theorem of calculus can be thought of as being about this formula that you might, want to instead think of as basically being f of b minus f of a, and you can see how that connects to the fundamental theorem, of course. I'm going to view this as an expression called change. I'm going to think of it as being a quantity, And in particular, the fundamental theorem of calculus says that if you have an integral, then you can compute your integral as f of b minus f of a. Namely, how much does your function, your antiderivative, of course, how much does that change? Right? F of b minus f of a. Okay, so what can we say about change? Why are we interested in change? And well, the point is that change is an accumulating quantity. Now, how can I persuade you that change is an accumulating quantity? I'm just going to give you a kind of a silly, obvious, relatable example. And let's think about, I like to think of my height as a function of time, right? And when I was a newborn, I was not very tall. And by the time I was 5, I was probably about like this, right? And by the time I was 10, I was probably, maybe about like this, right? So how much did my height change from age 0 to 5? How much did my height change between 5 and 10? Well, if you add those numbers, you're going to get how much my height changed between 0 and 10. Right? So the whole is the sum of the parts. Change accumulates over time. Does that make sense? Right? I mean, pretty believable, I think, if you sort of think it through. So we have an accumulated quantity, and again, that's what this says right here. The whole is the sum of the parts. And then now, of course, we rewrite that as this. You might recognize this more likely as df is f prime dx. Right? Sure, fine. And you can think of that in various different ways, and you can think of the, let's see here, you can think of this right there as being how much the function changed over a certain interval. And you can think of, let's see here, this dx as being the run, they very often call it. And so, f prime is the rise over the run, and thus the interpreting f prime as being a slope. Right? Sure, fine. There's nothing wrong with that. I want to take a different point of view, again, for our particular needs right now. Don't think of this as height per unit width or rise over run. Think of this instead as accumulating quantity. We've established that change is an accumulating quantity per unit size. Right? There's a certain amount of size here representing the size of a subinterval on the x-axis, and I want, of course, to interpret dx as how big that is. So when you think of it as quantity per unit size, we again come back to this familiar idea that you can interpret, well, I really am running out of colors. You can interpret this f prime as being a density. It's a little bit weird, right? An odd take on the fundamental theorem of calculus. I'm not saying this should be your only take. I'm not even saying this should be your first take. But for what we're doing right now, this is the point of view that I think is the most profitable. The fundamental theorem of calculus is a statement about this accumulating quantity called change and its associated density called the derivative. Okay. All right. Now, what does that buy us aside from, now we can claim that this looks a lot like our previous theorems? The good news is that this is something that we can interpret very conveniently in a way that will help us understand those previous theorems. I think this is I found this very persuasive myself. Let's just kind of draw a picture here. We've got, change, total amount that the function changes. Got a graph of our function f here. You can see the value of f starts off at that value, and then it ends up at this value. And so grand total, the function changed by that amount. And we measure that by looking at the endpoints, right? That's where we measure change. Let me scroll back to here. Y'all remember this page? And I gave y'all this real weird, uncomfortable seemingly almost implausible suggestion that circulation, even though circulation is computed on the boundary, that it actually happens in the interior, that seemed like a bit of a stretch, right? And I really admit that. So computed on the boundary, and I wanted to suggest that we should think of it as happening in the interior. So let's look now at where we were back here. Let's see, here we go. Check it out. Our accumulating quantity here, change, is computed on the boundary. But in this case, I don't think it takes any imagination at all for me to persuade you, but it happened in the interior. Well, of course it did. You can see it right there. Look at the graph. You can watch the function moving along its graph, changing on these values of x in the interior, obviously. Right? Think about when I went from age 0 to age 10, and my height increased by I don't even know how many inches that is. Did my height increase 50 inches exactly at age 10? Obviously not. No, come on, silly. Of course not. I mean, my height changed in the middle, in between ages 0 and 10. Right? So what I love about this, the comparison, looking at the fundamental theorem of calculus as an accumulation theorem, as being morally equivalent to Green's theorem, analogous, different, of course, for context, is that this intuition that we have right here, that, well, of course, the accumulating quantity happens in the interior. Hopefully that might make it easier for you to choke down this idea that seemed so weird at the time, a couple of days ago, that, this accumulating quantity that you compute on the boundary, you should think of this as happening in the interior as well. Right? Because this is just kind of a same story, different context, and you should be comfortable with that for reasons analogous to why you're comfortable with this. Right? Change happens in the interior here. So be open to the idea that maybe you can think of it analogously in the other context. Okay, so I think there's a lot of value with that. Now, related note, back here to looking at the fundamental theorem of calculus, how does the derivative figure into this story about change and where it happens? Well, the derivative is my density. Density tells you how much of the stuff is where. Where is it and how much? Right? So let's draw a picture of the density here, namely the derivative. So y'all remember your curve plotting stuff from way back when. So you can see, of course, the derivative is 0 along in here where the function's not changing. Then the derivative starts to increase, and then it kind of levels off, and we have a roughly fixed derivative for a little while, at which point it starts to decrease again, and then it levels off again and settles in at 0. So, flash back to Calc 1. Right? What I have in blue here is a picture of our derivative. Cool. And look at this. It is pointing exactly to where the change is happening. Right? Literally, the derivative, and again, of course it does. That's what the derivative's job is. The derivative's job is to tell us, well, again, in sort of Calc 1 terms, the slope, which of course means where the function's changing. So the integrand of my theorem, the density of my accumulating quantity, tells you where and how much of the quantity that you observe on the boundary, where and how much is that happening actually in the interior. All right, so likewise, Green's operator and divergence, they do the same thing for circulation and flux. All right, now let's see a silly algebraic example. I'm going to ask a ridiculously easy question here. We've got this function right here, f of x is x squared. There you go. Oh, well, let's try to do a better job with the... There we go. There we go. There's our function. And you can see right here that the total change is 9 between 0 and 3. Where did that change happen? Well, we've already agreed it happens in the interior, loosely speaking. But okay, let's look at these two specific points, x equals 1 and x equals 2. Is there more change happening at x equals 1? Or is there more change happening at x equals 2? Now, in this case, the picture tells the story. We don't need the algebra. We don't need fancy interpretations of things. I can just see, look at that, it's steeper here when x equals 2. But if I want to take an algebraic point of view on that, where the change is happening, we decide where this accumulating quantity is by way of its density being the derivative, right? And I can compute the derivative and I can plug in my two given points. I want to know, is there more of that happening at 1 or at 2? And just see where the function's bigger. See where f prime of density is bigger. Between these two, which of these numbers is bigger? Well, obviously, this number is bigger. So at the point 2, there is more change happening. Right? More of the change is happening at 2. Right? That makes sense? Everybody good? So now, I call this a silly example. It's perfectly obvious how this is going to go down. But it's perfectly obvious because we have a picture where everything is just right there staring at us. Right? But what we have then, you might say, is this is a geometrically easily confirmable example of how to use density to tell you where stuff is happening and how much. Right? So density, aka the derivative, is what algebraically tells us and quantifies for us how there's more happening at x equals 2 than there is happening at x equals 1. Okay. All right, so we're going to eventually do the same thing for circulation and Green's operator. For the moment, let's keep it geometric and look at this example. We have a curve that is a boundary, of course. There. We've got some vector field representing a flow. Let's say a flow of a fluid. Why not? Let's talk about circulation. What's the total circulation here? Well, look, as I go along the top here, looking at these pieces, as I move along the top, measuring line integral as I go along the curve. I'm going this way along the curve, but the fluid is going that way. So to what extent is the fluid flowing along the curve? Well, kind of the opposite. Frankly, right? It's going the wrong direction, so negative line integral. You're expecting, as you go this way along the curve, as you perform that integral, as you go this way along the curve, you're going to get negative values on that top edge. By comparison, look down here, right? These terms along in here. Here, the fluid, as I'm going along the boundary, the usual way, the fluid is flowing along the curve, second direction. So I'm going to get negative line integral from the top edge, positive line integral along the bottom edge. How do they compare? How do they add up? Well, the field vector is shorter up here and longer down here. So this is going to be a relatively small negative, a relatively large positive. That adds up to positive. Right, so we've got a positive amount of circulation total. And now I'm going to ask the usual question. We have this this positive amount of circulation right here. And, of course, we measured that by looking at the boundary and along the boundary. But where is it really coming from? Where is this circulation happening? What's the source of the circulation? And, well, look, it's not here. That general area right there, there's no circulation coming coming from there. Remember, you can think of circulation as, if you were to drop a leaf into the stream, and how does, as the leaf sort of flows downstream, does it just flow downstream like this, or does it sort of spin and turn? I can't do that with my hand very well. Does it spin and turn as it flows downstream? So I would argue, just kind of look at the picture, across the top of this leaf, it's being pushed in a way that would spin it clockwise. But across the bottom of the leaf, it's being pushed in a way that would spin it counterclockwise. It's the same amount on both top and bottom. There's a symmetry to this. And basically, I think those are going to cancel, and this would just this wouldn't spin at all as it's going along there. So you can confirm this with Green's operator if we had a formula for this vector field. We don't, but if we did. And that, in that vicinity there, if you were to compute Green's operator, you would get 0. And likewise, down here, you would get a 0 there, too. Now, a little surprising because the vector field's different down here. It's longer. We have stronger flow down here, but equally strong, again, on top and bottom. So you wouldn't expect the leaves to be spinning there either. But here's what I think would happen if you were to look in the middle, right? If you look in this region over here, so let's say kind of like this or so, well, there's a flow happening on the top that's going to tend to want to push it clockwise. There's a flow, which you might say along the bottom, that's going to want to push it counterclockwise, but it's stronger on the bottom and weaker on the top. And so again, it's going to be one of these sort of competing forces, but the bottom's going to win out because that's where the vector field is a little stronger. And so I think this leaf, this little blue leaf right here, I think that as that floats downstream, I think it's going to be spinning counterclockwise. Everybody buy that? That seemed physically, kind of geometrically satisfying? Well, I claim all of this is going to be confirmed. Again, if you had a formula for this vector field, and if you could write it down and compute Green's operator, what you would find there is that Green's operator in the gray area would be positive. So, again, to the question, we got this circulation. We know we have a positive total circulation around the boundary. Where is that circulation happening? It's happening in the interior. And Green's operator tells me where and how much. In this gray area where Green's operator is going to be positive, yeah, that's where the circulation that we're measuring on the boundary is coming from. It's got nothing to do with what's happening up here where Green's operator is 0. It's got nothing to do with where down here where Green's operator is 0. In the same way that, where's this change happening that we see in this function? Well, it's got nothing to do with what the function is doing way over here on the far left. There's no change happening there. And likewise, nothing to do with what's happening way over on the far right. Is that cool? So, in the same way that the derivative, aka the density, allows us to see where and how much of the change is happening between a couple of points we might want to compare. Likewise, Green's operator is algebraically going to do the same job for us concerning circulation. So if you're interested in oh gosh, I'm in the wrong mode again. If you are interested in circulation, you got some wacky vector field here, right? I have no idea what this vector field looks like. It'd be real hard to draw a picture. In some sense, my whole motivation for making an example like this is so that we can't draw a picture. Let's see how we'll answer the question without having any geometric intuition for it. Whatever that circulation is, it's coming from the interior, and our density, Green's operator, is going to tell us where and how much. Here's Green's operator. You can plug in Green's operator at the 2 points that we're interested in, right? So we're interested in comparing what's happening at 3, 3 with what's happening at 2, 4. Okay, so we plug those in, right? And you want to know where is more of the circulation happening? Well, okay, well, look at the number that is more. 28 is more than 22. And that means that there is more happening at the point 2, 4 than there is happening at 3, 3. Both are contributing. You can see right here with the numbers. Both of these points, what the vector field is doing at each of these points is contributing positively to the circulation. But more so at 2, 4, less so at 3, 3. Does that make sense to everybody? Now, likewise with flux, and you can talk through the picture on the previous page. And the punchline is, again, it is that if you're interested in flux, flux density is going to tell us where and how much it's actually happening. Flux density being divergence. Divergence is easy to compute. You can plug in our 2 points. Oh, let's see here. These 2 points, 3, 3, and 2, 4. Plug them in, and well, where is there more happening? Well, there's like 17 is more. Right? That's where the flux density is greater. So there is more of the flux originating from the point 3, 3 than there is from the point 2, 4. Is that cool? Everybody buy it? All right, so again, I'm a big fan of the idea of analogies, especially when we're talking about ideas that are, oh my gosh, so geometrically challenging, right? And we're trying to make sense out of circulation and flux and vector fields, and we can't draw a graph. There's not enough dimensions to draw a graph. It is very geometrically challenging. Being able to make clear interpretations of, where's my thing? Being able to make clear interpretations of the objects involved in the equations is really important. And again, that's where this business about this business about seeing how the fundamental theorem of calculus really is another accumulation theorem is so beneficial, because intuition that you have for how is the integrand a density. How does the density point to where the accumulating quantity is happening? This easy intuition that you can develop here, looking right at the graph, this intuitive experience with what is change and where does it happen. All that you can digest here, you can interpret analogously for Green's theorem, Green's operator, the 2D divergence theorem, flux density, right? Free interpretations that come from focusing on those analogies and those comparisons. Okay. All right. So I hope you'll find that useful. We're going to move on now to 6.3. Oh, I'm sorry. Question.
Yeah, sorry. On the picture that you had, can you point out flux density and circular density?
On this picture right here? Yeah.
Then the circular density is what you were referring to when the beam's turning.
Yeah.
Different vector sizes.
Yeah.
In this case, is there flux density?
Yeah, absolutely. So, I mean, let's look at a couple of pieces. So I claim there's a grand total, a positive amount of flux, because there's sort of negative flux on this side, small negative. This is big positive, right? So, okay, but where in the interior is it coming from? And I would argue it's pretty clearly not coming from anywhere over here, because there's just as much flow into that green zone as there is out of that green zone. Again, it's just you can almost imagine pieces of water, and every water that flows in flows right back out, right? Okay, so but what about over here? Well, oh gosh, I hit the thing. What about over here? Well, same story, same in, same out. Smaller, but same in, same out. But if you ask that question now here, well, there's a little bit of a flow inward, but there's significantly more flow outward. And so you're going to get negative boundary flux on the left side, small negative, on the left side, large positive on the right side. So grand total in this general area, there's a positive amount of flux, and you can see it from just literally looking at the flux for that particular piece.
Circular density there is 0.
I'm sorry, one more time?
Circular density there is 0.
Yeah, that'd be right. I mean, we need to know the formula for the vector field, but yeah, based on how I have it drawn and sort of interpreting, yeah, I would guess circulation density would be 0. In fact, I would guess that'd be the case for everywhere for this vector field.
So it's two different types of motion.
Two completely different things. Yeah, circulation and flux they're not the same. They're not complementary. They're just different. Yeah. So to answer your original question, I think in this left white region here, I think divergence would be 0. In this middle region, I think divergence would be positive. And in this right region, I think divergence would be 0 again. And so again, where the divergence is positive, to speak more sort of broadly, where the density is positive, that's where the stuff is, right? So flux that you collect on the boundary is coming from this gray region in the interior. Yeah, awesome. Yeah, good. Okay, so 6.3. Accumulation theorem number 5. You might say. Called the fundamental theorem of line integrals. If you skip down here to the end, you can see why they call it the fundamental theorem of line integrals. It looks just like the fundamental theorem of calculus, doesn't it? Integral is f of b minus f of a. It's practically a ripoff of the fundamental theorem of calculus. Okay. But of course, the difference is that this is about a line integral, right? See it right here. There it is. That's a vector line integral. So thus the name fundamental theorem of line integrals. If you wanted to get real quibbly, you could call it the fundamental theorem of vector line integrals, but there's no need to make that distinction. Okay, so this is a new theorem. Again, there's different points of view you can take. There's different ways that you can prove this. My goal, I'm going to remind y'all, just, why are we approaching things in the way that I am here? My goal is not to prove the individual theorems as quickly as possible. My goal is to present them from the point of view that most demonstrates what they have in common, right? Because I want y'all to, my big takeaway, when y'all are looking back at this course 5 years from now, 10 years from now, whatever, what I most want y'all to remember is how all of these theorems are basically the same idea, different details because of different geometry, but that they're still basically all about the same ideas. Okay, so that's the point of view we're going to come from. Again, we're talking about an accumulating quantity, and the accumulating quantity is change, just like with the fundamental theorem of calculus. You see it right there, f of b minus f of a. This is the quantity in question that we're going to view as accumulating over the interior. Okay, now I need to persuade you that this is an accumulating quantity. This is a little bit different because here we're talking about it accumulating over a curve instead of accumulating over an interval on the x-axis. So does the fact that this is a curve, the fact that it's all wiggly and wambly and stuff, does that change the fact that it accumulates? And it does not. And here's my example, my sort of motivating metaphor. Let's imagine this is a mountain road, as we often have. Let's imagine that what we're interested in is altitude as we drive along the mountain road. Well, there's an altitude at this point. There's an altitude at that point. I can talk about how much altitude changed as I drove along the road between those 2 points. There is also an altitude at this point, and I can talk about how much my altitude changed along that path as well, curvy though it is. And I hope nobody's surprised if I say that, look, if you gain 1,000 feet of altitude over the first part of the curve, and if you gain 1,500 feet of altitude over the second part of the curve, Well, grand total, you gained 1,000 plus 1,500 feet over the entire curve. Is that believable? If you want to see the algebra, you can write that down like so, like I have written on the right here. But I think there's a potential for algebra to distract you away from the intuition. And I think the intuition is pretty satisfying. Total altitude change is, yes, of course it is, the sum of the little pieces of altitude change that you gain as you go. Okay. All right. So we have an accumulating quantity. Let's talk about density. I'm going to remind y'all of this formula here. Well, this is a version of, anyway, a formula we saw back in Chapter 2, namely that dot product of the gradient is what allows you to turn input changes into output changes, right? And so if you displace your position by dx, and you want to know correspondingly what is the corresponding change in your altitude, dot product of the gradient. That's what does that. Again, old news, Chapter 2. And now I'm going to tweak that a little bit. I'm going to tweak it by rewriting dx in one of the ways that we have already established. Again, this is a flashback. I guess this is a Chapter 3 flashback. But we previously established that dx is TDS. And when you write it like that, now what we have is quantity relating over here to size, right? ds represents the size of a little piece of curve that you might be driving along. D delta represents the change in altitude along that piece of road. And therefore, gradient dot t, whoops, I missed the gradient dot t. This is our density. By the way, temporarily, let me scratch this stuff up. We're going to come back to this in a couple of minutes, but for the moment, let's not look at that just yet. And let's not look at this just yet. Okay, how we doing? Everybody with me? So, old formula from Chapter 2, rewritten accordingly. We've got quantity per unit size. Therefore, this gradient dot t is our density. And it's all over but the shouting. So let's put it all together. Oh gosh, and I'm in the wrong mode, of course. Putting it all together. Change accumulates. If you like, the total altitude change is the sum of all the little individual altitude changes as you go along. Total is the sum of the parts. And as I have above, output change relates to input displacement by way of that density. Change density, we call it, of course, because our quantity in question has changed. Okay, what do you think? Notice how the pattern, right? I mean, so the argument that we made about mass, it was morally equivalent to the argument we made about circulation and boundary flux and change in the fundamental theorem of calculus, and now change in this new theorem that we're developing. It's always just a matter of noticing, hey, we have an accumulating quantity, and by hook or by crook, we come up with an idea of what the associated density is and theorem. And the one last little thing that we need to do here, let me just get rid of all that, is to just remind ourselves that, well, of course, TDS is dx. And so here's our big theorem then. There's our new fundamental theorem of line integrals. Vector line integral of a gradient is f of b minus f of a. And we've proved it. Now, we are kind of out of time at this point, and rather than try to, squeeze something in at the end, I'm going to leave off all this stuff that I've got scratched out. I'm going to leave that for next time. So that's where we'll pick up on Wednesday, and see y'all later. Have a good one. And I should have exams returned with this curve and everything tomorrow morning. So be on the lookout for that tomorrow morning. All right, see y'all later.